Okay, I'm back. We've been discussing how sampling produces an infinite copy of spectra in the frequency domain. And this is kind of interesting because on the one hand, you don't really see it, right? If something had infinitely many copies, you would expect it to have infinite energy. And that just seems kind of strange. If you have infinite energy, then how can you represent it with a few finite samples? So there are some philosophical aspects to this. However, it is true that when you evaluate the DTFT of a signal at frequencies separated by 2 pi, you do get these other phantom copies. And everything is described in terms of how sampling behaves, filtering, and other actions are all well described by utilizing these multiple copies. So, what I've got drawn here is a single continuous time spectrum. It's band limited to B, so the frequency spectrum is 0 outside of plus or minus B. When we sample it, several things happen. One, the amplitude is scaled. So the amplitude was A, now it's A over T. One way to intuitively think about what's going on here is that we do have energy in the discrete time domain. If we have a smaller sample period, then we get more samples that contribute to this signal, or fewer, depending on how many we use. But the most important thing to note is that we have this in our DTFT. We now have this BT scaling here. So the discrete time signal, if we were to put little omega into this formula for xc of t, we would see that it evaluates to b at that point. So that's how the scaling manifests. And then the fact that we have multiple copies shows up like this. We could add perhaps some useful points onto this plot, 2 pi and minus 2 pi. Since the signals are replicated there, it's in order to make sure that we don't corrupt the signal, we really want to make certain that we don't have overlap. Okay, so what happens if B is much larger? If B is much larger, then it would be out there. But the same thing would happen to the other frequency components. And unfortunately, that would give us a region here and a region here where the primary spectrum overlaps with one of its phantom spectra. Another way, there are different ways that you can view this. It's all the same math and it just comes out to manifest in different ways. You could also view this as this part of the spectrum is reflected and added back into itself over here. But no matter how you slice or dice it, we get a corruption of our principal copy of the spectrum if we're not sampling sufficiently high. And we've already discussed the sampling theorem. So this happens if t is greater than pi over b. Another way of looking at that same thing would be b is greater than pi over t. So b is a the continuous time frequency in radians, and it's saying that the continuous time frequency, we get aliasing if it's greater than or equal to, and I haven't really, it's, in this example we've gone down to 0, so the equal to doesn't really matter, but in general we have to keep that. It's greater than pi over t, or in other words, f max, which is equal to b over 2 pi, is greater than sampling frequency, which is 1 over t divided by 2. So in any of these cases, which are all the same, we have aliasing, or a corruption of the spectrum by one of the copies that appeared. Okay, but let's assume for now that we don't have this aliasing, that we've sampled quickly enough. The next step is to figure out how to reconstruct. Now we've already done that. We've shown that you can do a reconstruction of the spectrum using the sinc function, and then I discussed that, well, the sinc function is great, it's ideal, it works just like we want it to. It's also infinite in extent, and so infinite. We have a signal with infinite extent, and each sample has to be reconstructed by copying in a sinc function, as we talked about. Then we have an infinite sum of infinitely long things, and that becomes, and we're concerned about the computational cost here, because we really want to do these on a computer, and infinite sums of infinite things becomes tricky. So we had some function like this where g was our sinc function, scaled appropriately by our sample period, and that was our reconstruction formula. Okay, let's investigate this a little bit further and see where else we can take it and how it can be used. So if that's xr, then we can take the continuous Fourier transform and sum over n again, x of n. It just remains as a scaling factor because we're taking the Fourier transform with respect to the continuous time variable little t. So that becomes j omega, and this phase term shows up because of the minus nt of our original gt. So there we go, we have our Fourier transform. Now the Fourier transform is not a function of n, so it can come out front. We're left with this infinite sum, x of n e minus j omega n capital T. What to do now? Well, let's do a change of variable. Isn't that what we have learned to do? And so here, if we define little omega is equal to capital Omega T, then this is the DFT spectrum, or DTFT. Of x of n. And of course, that is going to dilate said FFT spectrum. So we're just showing this as a way of visualizing what's going on. We now have G, the spectrum of our original, the spectrum of our reconstruction function, nominally a sinc function, multiplied by the DFT spectrum. Okay, so let's write this final expression here as, and I've kind of run out of room, so I'll stick it over here. XR j omega is equal to GT, where G is our interpolation function, multiplied by EJ capital omega t. Keep everything in the same variable here. So what's going on? Well, as you might recall, the spectrum of the sinc function is actually just a rectangular box. And of course, the DTFT spectrum now has these infinite copies. So let's put these things together and observe what's going on, and this will give us a little more flexibility to explore other functions that we might use instead of the sinc function. So copy that and put it into here. And so what do we have? What we have in this first line is our, doesn't deserve red, we'll just go blue, the DTFT spectrum. The second line is said DTFT spectrum now converted to a continuous time signal. So and I'm going to have to come back to this because I think I haven't sufficiently explained what's going on. So far we've done the math, but this seems, what exactly does this represent? Where we have x of t based on our samples, but now looking at the continuous time spectrum. And so I'll come back to that in just a minute. Of x of n t. Okay. Hold on to that. So we take that spectrum and we multiply it by our interpolation function spectrum. And what we get out is a continuous time signal spectrum that matches what we started with. Okay, so that's basically what's going on. So let's go back and look and fill in those steps that I promised I would do. This is a spectrum of a sampled signal. To create a continuous time signal, we nominally go through several steps. The first step is we need to take these individual samples indexed by n and throw them back into the domain of a continuous time signal. However, to start with, we still have samples. So how do we do this? It takes very specialized hardware that doesn't break down when it has infinite things on it. We put now, and the difference here is usually Kronecker delta functions are denoted by kind of these lollipops, and Dirac delta functions are denoted by arrows, indicating that they're infinite in height. So where we before had scaled Kronecker deltas, 1 per sample, we now have scaled Dirac delta functions, 1 per sample. And so that's the intermediate step. Next, we filter this sequence of Dirac delta functions with our filter. So we're going to convolve that with our g of t, little g of t function, and that will give us our continuous time signal such as it is. Okay, so that's what's going on here. Now in practice, actually it might make sense to throw a bunch of spikes out and then filter them, but you can imagine there might be other ways that one could recreate a continuous time signal from a discrete time signal. And so we can look at approximate interpolation approaches, but we can look at them now from the view that whatever our approximate interpolation function is, we are filtering our sequence of impulse responses with this filter. And so we can consider what's going on in the frequency domain. So approximate reconstruction techniques that are common replace g of t from being a sinc to being something else. So let's say we had our sequence of samples. Can't see the one that scrolled off the page, so we'll put in some other ones here. There, a nice little sequence of samples, and we want to reconstruct the continuous time signal. One way to do this is what we call a sample and hold. So this gives us a signal that's stepwise continuous. And you can imagine doing this in hardware. You just set the output voltage at a certain level, determined by the sample height, for a one sample period. And when the next sample is you're ready to output it, you once again change it to, in this case, another sample, the height of another sample, and away we go. So what's going on when we do this? If we do the sample and hold technique, it gives us a g of t that's a sinc in the frequency domain. So now we're filtering, instead of isolating a single copy here at the baseband, we end up getting a signal that if we were filtering this with a sinc, would capture parts of the neighboring spectra actually infinitely, although it dies off as you get further along. And so now the frequency content is both distorted because the passband isn't flat, and it's also distorted because we've added in frequency content from these 2π replications. So This gives us, in the frequency domain, it gives us a sink. So maybe that's not the best idea. And what else could we do? We could do linear interpolation. Linear interpolation seems a lot nicer, and indeed it is. The frequency domain version of a linear interpolator is the transform of a triangle function, which is basically a sink squared. But a sink squared is nice in that these lobes here die off much more quickly. But we're still distorting the spectrum and introducing additional things. Well, there's a variety of things that we could use. In essence, whatever we choose as our interpolating function, we can think of it as the impulse response of some filter in the frequency domain, and so we want to choose something that makes sense. One of the best ways to make sense of this, or to make this work with approximate techniques, is to ensure that you are significantly oversampled. So what do I mean there? Well, here we have some space, kind of extra space. So if in this particular case we had a filter that was flat and then kind of ramped off like that, because this ramp part corresponds to where there's no signal energy, this would still give us an ideal output. So if you're old enough to have ever purchased a CD player, you might see that many of them have on there as one of their selling points that it's oversampled. What do they mean by oversampled? By oversampled, they mean they do some digital manipulation of the signal and upsample it so that by the time it's actually put out to the analog to digital converter, you have a large gap, allowing them to use a very cheap filter in the reconstruction, one that is not made to very high specs. So I've always found it interesting that one of their greatest selling points is something that actually enables them to make a cheaper product by doing, in this case, more of the processing in digital, making the analog electronics much cheaper and simpler. Okay, so one last thing I want to talk about with respect to this, and that is, actually I think I'll save that for some examples that I'll talk about next Tuesday. So we'll consider this lecture done, and I will talk to you again soon. Thank you.